Hello students, this is Professor Chalai, and in this video we're going to look at the uncertainty principle. As always, you can follow along with our Chapter 6 workbook, and by the end of this video you should be able to calculate uncertainties using Heisenberg's uncertainty principle. Now, in our previous video, we looked at the de Broglie wavelength. We talked about how the discrete line spectrum of molecules can be explained not by the Bohr model of the atom, but by describing the movement of electrons as waves trapped in the field of the atom. And so by doing that, the energies will be very discrete, and so that's why we get line spectrum. And then using the de Broglie wavelength, we can assign the wavelength of that electron moving as a wave. And in fact, the de Broglie wavelength can be used to describe the wavelength of any massive object with some velocity. But there's an interesting phenomenon that happens when we start to describe things by as waves. For example, well, let's just take the de Broglie wavelength again, right? It's h divided by m times v. M times v is the momentum p. So if we rewrite this equation to solve for the momentum, we get the momentum is h over lambda. So the momentum of a wave, which describe is the mass times the velocity, describes how fast the wave is moving, is dependent on the wavelength. So let's say we have some sort of box or something where we have a wave trapped in inside, and we have a wave like this. Let's end the wave there. Okay, we can calculate the we can calculate the wavelength of this wave pretty straightforwardly, right? Like maybe from here to here, that will be our wavelength. And so because we can find the wavelength pretty accurately, we can also find the momentum pretty accurately, right? So momentum, check. We can calculate the momentum of this wave. But what about where, if this was an electron as a particle, where is the electron in this box? The red line is the wave for the electron and how it moves, but where is the electron? Is it over here? Is it over here? I mean, according to this, it's everywhere, right? So the position, we don't know where the electron is. The wave is everywhere. Now let's look at the other situation where we have the same box, right? And we say that the position of the electron is right there, right? So we have position, check, we know where it is. What's the momentum? Well, to calculate the momentum, we need to figure out what the wavelength is. But what's the wavelength of that little dot? We don't know. So this is very simplified, by the way, in how we can use waves to determine momentums and position. The position one is a little bit more complicated. We actually have to use lots and lots of waves to determine the position, but I just simplified it with a dot. But all that is to say that if we have waves, we can either know the position or the momentum, but not both at the same time, right? So with waves, we can know either one, the position or momentum, or not, but not both at the same time. And if there's some there will always be some uncertainty in either the position or the momentum. And so in this equation for Heisenberg's uncertainty principle, the delta represent the uncertainty, right? So x, just like the x-axis, is a position. So delta x is just the uncertainty in the position. M is the mass. We're certain about that, right? Mass of the electron, or your mass, or whatever we're dealing with. And then delta v would be uncertainty t in velocity. So the uncertainty in the position multiplied by the mass times the uncertainty in the velocity will always be greater or equal to this factor of h over 4 pi. So really, we cannot get more certain than this factor. If this factor was 0, it means that we knew one of those quantities to absolute precision. Their uncertainty was 0. If any of these uncertainty were 0, then this value would be 0, right? But that is never the case. It's always going to be greater or equal to h over 4 pi. So because it's going to be greater or equal to h over 4 pi, we can always use h over 4 pi to calculate the minimum uncertainty. Because the maximum uncertainty could be, well, we don't know, it could be very large. So we can use this equation to calculate the minimum uncertainty either in the position if we know the uncertainty in the velocity, or the uncertainty in the velocity if we know the uncertainty in the position. Let's see some of this in action. Let's look at number 13 and see if you can try to calculate it on your own first, and then I'll go over it with you. So here we're asked to calculate the minimum uncertainty in the position, or delta x, of an electron. So it's an electron, so we already know the mass, right? We learned about the mass of the electron earlier. And they tell us the uncertainty in the velocity of delta v is this value. So let's look at that. The uncertainty in the position times the mass times the uncertainty in the velocity is h over 4 pi. We want to calculate the uncertainty in the position, so we divide both sides by m and delta v, so we'll get h times 4 pi times m times delta v as the minimum uncertainty in the position. And now we're just plugging in numbers, really. H is 6.626 by 10 to the minus 34 joules times seconds, or in this case we'll use the other units, kilograms meters squared per second, divided by the 4 pi, right, that's important, times the mass of the electron, which we know as, what is the mass of the electron? 9.109 by 10 to the minus 31 kilograms. So that kilograms will cancel out, times the uncertainty, delta v, the uncertainty in the velocity, which they give us as 6 by 10 to the minus 6 meters per second. 6 by 10 to the minus 6 meters per second. So per second cancel with per second, the meters cancel with one of these meters, and the answer that we'll get will be in meters, which makes sense because this is a position calculation. And here, if you plug these in your calculator, you get 10 meters. So if you have an electron moving very, 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 very slowly, or rather the uncertainty in the position velocity is very, very small, meaning we are very sure of how fast it's moving actually, then we actually don't know where it is. It could be anywhere in some 10-meter length of distance, which if you think about it, 10 meters, about 10 yards, it's the length of a room. So if we're pretty sure of how fast this electron is going, we actually don't know within the space of a whole room where that electron actually is at any point in time. Okay, let's look at number 14, and let's say that it's asking us to calculate the minimum uncertainty in the position of a person in a car. Your weight of you in the car, let's say it's 100 kilograms. Ignore the speed because that's the speed of the car. Let's say the uncertainty of the speed of the car is, I don't know, your speedometer is pretty accurate, but let's say we're uncertain of how fast you're going to 1 meter per second. That's your uncertainty in the velocity. Spend some time trying to solve this one, and when you're done, you can unpause and we'll go over it together. Okay, so let's look at this. Again, we know that the uncertainty in the position times the mass times the uncertainty in the velocity is h over 4 pi. Or greater or equal to h over 4 pi. But we're calculating the minimum uncertainty, so we can set this equal to h over 4 pi. Okay, we want the uncertainty in the position, so that's delta x. So let's put everything else over on this side of the equation. So then we'll get delta x is equal to h divided by 4 pi times m times delta v. So now we just need to plug things in, right? H we know is 6.626 by 10 to the minus 34 kilogram meter square per second. 4 pi, right? 4 pi doesn't go anywhere. The mass of you and the car together, we said was 1,000 kilograms. I just did that so that the numbers could cancel out nicely. And I said the uncertainty in your speed, because your speedometer might not be that accurate, let's say, is 1 meter per second. So per second cancel out, meter cancel out with one of the meters. This will lead to an uncertainty of your position of 5.3 by 10 to the minus 38 meters. That's a very, very, very small uncertainty. So if you're traveling down the road, um, you know, you might be you might not know how fast you're going precisely, but the uncertainty in your position is so tiny that it doesn't even matter. You know exactly where you are at any point in time, is what I'm trying to say. Okay, so that's the crux of the uncertainty principle. Because things are described as waves at their most fundamental level, it means that we can't know the position or the velocity of something at the same time, because the way waves are used to describe position and momentum are different, right? A momentum wave means we know the wavelength, but that means that the position could be anywhere along this wave. We don't know where it is. On the other hand, if we're trying to use a wave to describe a position, we a specific position, then we don't know what the momentum of that wave is, because we can't really find the wavelength of that wave. So that's how they're related, and so we can use that then to find uncertainties in either the position or momentum of electrons in atoms, or of you driving up down the road. All right, that'll bring us to the end of the uncertainty principle. It's a very brief introduction. When we come back in our next video, we're going to go deeper into the quantum mechanical model of the atom, when we start to look at different orbitals and energies and different sorts of other different things. We'll see you then. Bye.